Welcome back to the last part of Scale Invariant Feature Transform. We are in fact almost done with the Scale Invariant Feature Transform, except one step. That's what we would finish it off in this current class, maybe in the first 15 minutes itself. So again, looking at the overview of the Scale Invariant Feature Transform, this is a one way of representing different modules in it. So we started first with, as we are more keen on what is completely novel compared to what we have seen earlier in case of detector. So we started with key point orientation stuff so that the descriptor becomes invariant to rotations. Then how to build the key point descriptor we have seen. Of course, this would be the future work we would do, how to play with the features that you obtain. So nothing to worry about that as of now. And then we started from the beginning. So basically this forms your descriptor, this is your alignment part, and the rest whole thing is detector. Then we move to detector. So in detector we noticed that Laplacian of Gaussian is something that helps you in finding out edges. And then we have also seen that this Laplacian of Gaussian can be efficiently computed using difference of Gaussians. That's a very computationally efficient approach. So we constructed a scale space in sigma, then take difference of Gaussians, then locate extremas in difference of Gaussian. So for a given pixel, you look at all scales of sigma, which is the maximum one. And after that, we further locate subpixel locate potential feature points at a subpixel level when you see spatially. And also the same thing as we are considering discrete values of sigma, then Taylor series, with the help of Taylor series expansion and a curve fitting, we figured out how we could arrive at uh, an extrema. And followed by that, what we have also did is you normalize these values of these extremas then to 0 to 1, and anything less than, I think it's 3% or 4%, you would drop them as extrema points. So that's what we have done. And the last step now remaining for this class and for SIFT discussion is filtering edge and low contrast responses. And of course, this low contrast response, in a way, we have done it the moment you are putting a threshold on the Gaussian. So any questions so far before I move to the last remaining leg of this scale invariant feature transform?
Sir, just one question. The scale space, like whatever you're talking about,
Hmm.
what exactly, could you just quickly define that?
Yeah. So when we say scale space there, you have you are looking at a different scales, the extremas. That's how you are changing your window size. So that changing your window size is looking at it different scales, whether it is a key point or not. That's what it intuitively means. And then how we are doing is to look at different scales is equivalent to looking at a larger window, or using a larger Laplacian of Gaussians there, and or different values of sigma you are computing the so if you recollect the graph that we were plotting, where you are varying your sigma, and then you are getting some graph like this of this function which is here Laplacian of Gaussian. So then you are looking at all its neighbors as well as for all values of sigma, and taking this as your the key point there. So that's what construction of the scale space is equivalent to all the octaves we discussed. So you first apply with sigma, sigma square, sigma cube, sigma power 4, so on within one, and then you resample it for computational efficiency. And now accordingly, now depending on the number of levels that you have considered in each octave, you would further resample, you figure out what should be the sigma value, and you repeat the whole process. And then you compare a given pixel with its surrounding pixels, as well as those pixels which are at different scales of sigma. That's what we mean by scale space there. This is regarding how you could further remove the outliers. So again, let me put here, for example, the Laplacian of Gaussians. Let's say if you consider the isometry. How is it? I always get confused with the name. So it is like 90 degrees isotropic. Laplacian of Gaussian kernel looks like this. So as we discussed, it has, suppose if you have a in your pixels that you are having where you are putting this and computing these values, suppose there might be an edge in this, so there might be a vertical edge is there, suppose. Okay, so then what would happen, this would give you a very high value. Assume that a very strong vertical edge is there. Assume that these are the values in the, when you are keeping it, let's say here, this pixel value is a, this also is a, this assume this is b, this is b plus 100, assume that. So you would get a very high value. Yeah, or it should be slightly differently, we need to work out it. Okay, this is not essentially even having an edge, because you are looking at these directions, could give you a very strong value here. Okay, this is not forget about these values, just look at this kernel there. So it cannot really, Laplacian of Gaussian cannot clearly distinguish between a strong edge versus a corner point. So something else is required. So it is for this purpose to figure out whether a given like a given increase in a large value in that is causing because of a corner or an edge. If you recollect from Harris corner detector, it does it by computing second order moment and looking at the eigenvalues of that second order moment, and from there figuring out whether these two values of eigenvalues we figured out there, they in fact represent the major axis and minor axis of an ellipse for a constant value if you look at it in the equation. And after that you are inferring how you could see that lambda 1 and lambda 2 both are large as well as both are equal. It does similar stuff here, but not based on second order moment, but by looking at the curvature that you would be getting there. And you all know, suppose when there is an edge, is there a very high curvature or a low curvature at that point? Suppose I have a surface there. Okay, assume that the intensities, the resulting intensities, I am plotting it as a surface. Suppose I have a sudden change in my intensities, do you expect a high curvature or low curvature?
High curvature, sir.
Right, that's right. It's in fact the second order derivative would give you the curvature. So the second order derivative would be very high. Now it does, so what it does essentially is, suppose you have just, it's not an edge point, but it's not a corner point, if it is just an edge point. So in the perpendicular direction, your curvature will be low. Again, this, so in order to compute the curvature, it takes the second derivative of your difference of Gaussians here. Whatever you are getting there, it takes second order derivatives of it and computes again this matrix here. So just to not confuse with second order moment, remember in the second order moment, you are taking something like dou I by dou x whole square, right? And then here dou I by dou x into dou I by dou y. Same thing here, dou I by dou x into dou I by dou y and dou I by dou y whole square. This was your second order moment. Notice there, in the second order moment, you would be in fact simply computing the first order derivative itself. So that's referred to as your second order, that you could in fact, we have also seen, I could have represented it as whole transpose also. That's the first order derivative itself. On the other hand, when it comes to Hessian, don't confuse that with this. Now you have dou square I. Okay, it's in fact difference of Gaussian, but let me for the time being put I itself, because what I want to draw your attention to is onto the derivatives here. So you are going to compute dou square I by dou x square here, and similarly here dou by dou y of dou I by dou x, and here the same thing, of course, dou by dou y of dou I by dou x and dou square y by dou x dou square capital I by dou y square. That is the Hessian matrix. So be very clear with the second order moment, where you are computing the gradient of I multiplied with gradient of I transpose in terms of vectors. Here, in case of Hessian, which has something to do with the curvature, and the curvature you get through second order derivative, you are going to compute this matrix here. And then for this matrix, this is again inspired with how the scale invariant how you do in Harris corner detector without directly computing the eigenvalues of it. Essentially, these eigenvalues now in similar lines of Harris would tell you about the curvature in the orthogonal directions. Okay, so it essentially does it in a slightly different way. Let me erase this out so that you be able to see what has been written here. Right. So here, what it does is, again, it is, I guess, is inspired from what Harris corner detector does. We again, so now let us call one as lambda1 and the other as lambda2. These are the two eigenvalues that you are going to get for this matrix. Then you look at the ratio of those two things, and again in similar lines to what has been done with the determinant and a trace. For example, when you write it as lambda1 lambda2 0 0 here, something like that, after having a, you could write it as a rotational matrix here. So you could make an inference here. For example, determinant of h would be lambda1 by lambda2, and here you would be trace will be equal to lambda1 plus lambda2 whole square here. Okay, now these two being equal and large enough, okay, you would figure out that this would have maximum value when lambda1 is equal to lambda2. Now again, lambda1 is referring to the eigenvalue with maximum value eigenvalue. This is the minimum eigenvalue that you are going to get. So in that case, when this is greater than 10, you will not consider it anymore as, so I leave it to you when, so essentially this has to be minimum, and that would eventually result in, this is a very simple math. You could in fact take first order derivative and make it 0, look at second order derivative. That much is good enough here. So essentially they are writing this as in terms of lambda1 by lambda2, not at all difficult here. Just take lambda2 common here, okay, and that would give you lambda, so that would essentially give you, well, 1 plus lambda 1 by lambda 2 whole square into, you have taken lambda 2 out, okay, and yeah, you could work out, this is very simple, and you would arrive at this expression. And after doing simple math there, you would figure out that this would have the optimal idea is lambda 1 and lambda 2 to be equal, is equivalent to r having a value of 1. And after that, if r is greater than 10, that means the ratio of lambda 1 and lambda 2 is very high, then you will not consider that anymore as a key point. Okay, so this is what you had got in the last class from 729 key points after localization of difference of Gaussians, and then applying a threshold on that with anything less than 4%, you are 0.04, you are dropping it. Now on it, you again now apply this, you compute this Hessian matrix, and on that, if your r lambda 1 by lambda 2 is greater than 10, okay, that's again empirically chosen that number 10. Other than that, there is not much interpretation to it. So those are the things that you would drop there. Okay, one quick observation you might make here is, in this house there are a lot of points here where you have a horizontal edge. Okay, relatively those points are reduced here. That's one quick observation you could do. In similar lines, there is one more vertical line here. For that also, you could make an observation here. but again, so you could go on and continue looking into it. And these are finally your key points. So with that, we are done with this block as well. Okay, and that, so this is at the end of this, whatever points you are getting, those are the key points detected from the scale invariant feature transform. And it is these key points that you would be for which you take a patch around it. Okay, 16 by 16 or whatever we discussed earlier, and then you find out the maximum gradient. That is where you are going to, I think it was in steps of 10 degrees you were, they were doing it. So, and then you are orienting finally into that direction. And after this orientation, you are building the key point descriptor. Again, there you are, if I'm not wrong, you are looking into the 8, right? You are dividing it into 4 cross 4. And for each region, again, if you recall, still remember, you are taking 8 directions there. And from that, it would eventually result in each key point is described as a 128 1 by 128 dimensional vector. So later, while you are comparing these respective key points, what you could do is, one simple case you could look at is what is the difference between the two key points. Okay, we are done with it. So if you have any questions, let's look into them now.
Sir, just one doubt. When you're computing the Hessian, like that matrix here,
Hmm.
H Hessian of D,
Hmm.
so I'll just, like, I had a small doubt. If we are computing this, we have one patch of image. First, we'll apply IX.
Hmm.
First, we'll apply IX. You will get one more matrix
Hmm.
based on that gradient.
Hmm.
Again, on that matrix, we are again applying IX. We are
Right.
again using that gradient.
Correct.
Now, this particular matrix is our IXX, and
Right.
now
That's
we
right.
are going to like sum up all the elements of this, right?
That's right. That's right.
Sum up all the elements. In the
That's
previous one, we just took IX and we sum up the square of those elements.
correct.
Is that
Exactly.
correct?
That's
Okay, sure.
absolutely right.
Yeah, sir. That's
So yes, so you are going to take now second order derivative and sum up. Earlier it was only square of your first order derivative. Now it is second order derivative summation. That is what you have here. We are done with this SIFT, and we will start a fresh new topic on the next class. Okay, this